Hello, good evening, everyone. I am Calvin Paul Joseph, a third year research scholar at the Institute of IIT Kharagpur. And today I'm going to conduct the week three's problem solving and doubt clearing session for the course State Space Approach to Control System Analysis and Design, taught by Professor A.P. Tiwari. So in this week three, sir has focused a lot about the state transition matrix, what are the properties of the state transition matrix, and how do we use it to find the general state space solution. Okay. So I will touch. So this is the outline of what we want to cover and on which topics we want to solve some sums. So that first is the state transition matrix (STM). Okay, so this can be for a linear time invariant system or a linear time variant system as well. Then how from the state transition matrix we have what is known as a zero input response, as well as there's a zero state response. This is the equation. Okay, and how we can use the state transition matrix and we can convert it to the state system matrix A. How now in the actual practical scenario, we will not have analog computer, okay, which is solving your state space equation and getting you the value. Usually, when it is being done in real time, there is a digital solver. Okay, so when you have a digital solver, what is done is the state space equations in continuous time is discretized. Okay, and there are two ways which we is there. One is there are two ways out of the many ways which we will look upon. One is the one using zero order hold, ZOH, and the other is using Euler's approximation. All right. Then also we will consider what is the fundamental matrix and what is the state transition matrix for a linear time varying system. Okay, so linear time invariant systems, their properties are very easy. They are nice and they are compact and mathematically it's easy to analyze. But once it becomes linear time varying, it becomes more complicated, etc. So I'll be touching upon one sum or a few sums for linear time variant systems as well. How do we find what is the fundamental matrix and what is the state transition matrix? Okay, so let's start with this sum. What is the system matrix say for the system with STM as shown here? Okay, I'll be writing some notes. So this is for week 3, and we'll be considering what is known as the state transition matrix, SEM. Okay, so we know for a LTI system, x dot is equal to AX. Okay, this is known as an autonomous system. And if there is an input, it will be represented as x dot is equal to AX plus BU. Okay, this is known as a non-autonomous system. So this is the general equation, but now we want to solve this equation. And after we solve the equation, then we can know how our states are varying with time. What is the effect of one input? How which state can be controlled, not controlled, etc. So we want to find a solution. We want to find how that state vector varies with time. Okay. So the solution, the state space solution is written as, or you can find it out as, this is from an initial condition, x of 0 is when t equal to 0. Okay. So x equal to e raised to a into t, x of 0 plus integration from limit 0 to t, e raised to a, t minus tau into b into u of tau into d tau. Okay. So this is the general solution. And this term This is known as the STM, or state transition matrix. Okay, STM. It is denoted by phi of t. Okay, and if you'll observe, it is represented here as well. So x of t is equal to phi of t into x of 0 plus integration from 0 to t phi of t minus tau into b u of tau into d tau. So over here the limits are for tau. Okay, tau is going from 0. Sorry. Tau is going from 0 to t as the integration is with respect to the variable tau. Okay, so this is the general equation, and to find the solution, we need to find the state transition matrix, phi of t. Okay, so let us assume we have excuse me. Okay, so this is the solution of the state transition matrix. So now what do we do with the state transition matrix? So we know state transition matrix phi of t is actually e raised to a into t. So how do you find this value of the state transition matrix? So if we have a is -1, 2, 0, 1. Okay. This is our state transition matrix. Then how do we find e raised to at? Can we write this as e to power minus t, e to power 2t, 0, e to power t? Is this the state transition matrix? No. Okay, this is wrong. This is not the way to find the state transition matrix. So then how do you find the state transition matrix? So one way is e to the power at actually is what? I plus a into t plus at square upon 2 factorial plus at cube upon 3 factorial plus at raised to 4 upon 4 factorial plus dot dot dot. Okay, so this is one way we can find. So we have to find I, at square by 2 factorial, at cube by 3 factorial, and so on. So this is known as a power series. So this is a power series. Okay. Now, the problem with this power series is it doesn't give you a closed form solution. It doesn't give you a closed form solution. Okay. So it becomes difficult to do. So there is another method in which you take the Laplace transform. Okay. So we know uh, if this is e to the power at, its Laplace transform is what? 1 upon si minus a. Okay. So what we should do is e to the power at actually is the Laplace inverse of si minus a inverse. Okay, so let us look at one example. So we have a is -1, 2, 0, 1. Okay. So what is si minus a? That is s into identity matrix 1, 0, 0, 1 minus a. A is what? -1, 2, 0, 1. -1, 2, 0, 1. So that is equal to s plus 1 minus 2, 0, s minus 1. So this is si minus a. Now how do I find si minus a inverse? So si minus a inverse is actually equal to, we just interchange this. So this becomes s minus 1, s plus 1, and we interchange the sign. So this becomes 2, 0 upon s plus 1 into s minus 1 into 0. Okay. So this actually is equal to s minus 1, 2, 0, s plus 1, 1 s square minus 1. So this is si minus a inverse. So si minus a inverse can further be written as 1 upon s plus 1, 2 upon s minus 1 into s plus 1, 0, and 1 upon s minus 1. Okay, because you're dividing each term by s square minus 1, and s square minus 1 can be written as s minus 1 into s plus 1. So that's why s minus 1 gets cancelled and only s plus 1 remains. Okay, so this is what we get. Now, we have to take the Laplace inverse of this. So first, let me write this further in a better way. So this can be written as 1 upon s plus 1, 0. Okay, and this actually is 1 upon s minus 1 minus 1 upon s plus 1 upon 1 upon s minus 1. So what I have done is this 2 upon s minus 1 minus into s plus 1. I have written it as 1 upon s minus 1 minus 1 upon s plus 1. So if you will do the partial fractions, etc., you will get this solution. Okay, so there is a certain shortcut which I learned in my bachelor, so I used it and applied it. Okay, so now we have this. This is by si minus a inverse. We have found this. Now I have to take the inverse Laplace transform. So what I will do, I will taking the inverse Laplace transform. So what I get, my phi of t is the inverse Laplace transform of Si minus A inverse. Okay. So that is the inverse Laplace transform of 1 upon S plus 1. Okay. Inverse Laplace transform of 1 upon S minus 1 minus 1 upon S plus 1. Then inverse Laplace transform of 0 and inverse Laplace transform of 1 upon S minus 1. Okay. So from this, we can write phi of t is equal to 1 upon S plus 1. The inverse of it actually is e raised to minus t. This is what e to the power t minus e raised to minus t. Laplace inverse of 0 remains 0 and Laplace inverse of 1 upon S minus 1 actually is e to the power t. Okay. So this is the system transition state transition matrix STM which was found for this A. Okay, there are other methods also are there, but this is the simple and easy way which I prefer to do it. Okay. So now we know the various properties of the state transition matrix. Okay, there are various properties. One is phi of 0 is actually equal to I. Okay, this has to be satisfied. So what we do, we put phi of 0 over here. Okay. So what do we get? E to power 0 is 1, right? So we get 1. This is anyway 0. Then here we get 1 minus 1, so it is 0. And e to power t, so it is 1. Okay, so this is proved. Phi of 0 is 1. Now, there is another property that is, phi of t is equal to e to power at. Now, what is the derivative of this? So, derivative we write as phi dot of t. That actually is equal to a into e to the power at. Okay, so that actually is equal to a into phi of t. Okay, so this is one property of the derivative of the state transition matrix. Now, there's another interesting property which we do. So, when you solve differential equations, you need to know the differential equations as well as you need to know the initial condition. Okay, so the initial condition is required for you to find what will be the later on conditions. Okay, so that is initial condition is very much important. So when you learn further and all, these are known as the boundary conditions, etc. So now, what will be phi dot of 0? What will be the phi dot of 0? That actually is what a into phi of 0. So what is that? That is a into your identity matrix, which is a. Okay, so this is another condition, another property. So this is property 1, this is property 2. Okay, so now let us verify this. So what I need to get? I need to get phi dot of t. So that is a derivative with respect to time of my state transition matrix, which actually is what? E to power minus t 0, e to power minus t 0, e to power t minus e to power minus t, e to the power t minus e to power minus t, and it is e to the power t. Okay. So now derivative of e to the power minus t is minus of e to the power minus t. Derivative of 0 remains 0. Derivative of e to the power t is e to the power t. And here it becomes plus e to the power minus t. And here it is e to the power t. Okay. So this is my phi dot of t. So now let me put t equal to 0. We'll put t equal to 0. So what is my phi dot of 0? Again, e to power 0 is 1. This is minus 1, 0. So 1 plus 1, 2 and 1. And if you will look back, this is my A matrix. Okay, my A matrix is minus 1, 0, 2, 1. Okay, so this is my A matrix. So this is actually my A matrix. Okay, so this is another useful property which you will use. So in the assignment also, there's one question which exploits this property. Okay, so derivative of the state transition matrix at 0 is equal to A. So this is another useful property. So now let us consider one sum. They're saying what is the system matrix A for the system with state transition matrix given as this. Okay. So we have just solved that. So we will look into this. Okay. So this is my question 1. Okay. What they're saying is my state transition matrix is given by 1, 0, minus 1, 2. That is 1, 0, minus 1, 2, e to the power minus t, e to the power minus t plus 3 minus 1, 0, 1, 3 minus 1, 0, 1, t into e to the power minus t. Okay, so this is the state transition matrix and we need to find A. Okay, so how do I solve this? So first what I'll do is I will find the time derivative of the state phi dot of t. Now what is phi dot of t? It is 1, minus 1, 0, 2. They don't have any time. So they are like a constant. So it's the derivative of e to the power minus t. So d of dt of e to the power minus t plus 3 of minus 1, 0, 1 derivative of t into e to the power minus t. Okay. So I like you many will know, but I just want to do it in a good way. So you can refer. What is the derivative of e to the power minus t? The derivative of e to the power minus t is actually what? Minus of e to the power minus t, right? So this color is not good. Then what is the derivative of t into e to the power minus t? Okay, that is t into the derivative of e to the power minus t plus e to the power minus t into the derivative of t. Okay, so that is equal to minus. So that is equal to t into minus of e to the power minus t plus e to the power minus t into 1. So that's why it is minus t e to the power minus t plus e to the power minus t. Okay, so this is your phi dot of t, right? So this is the derivative of these things. So we will write the phi dot of t is equal to 1 minus 1, 0, 2 minus of e to the power minus t plus 3 minus 1, 0, 1 minus t e to the power minus t plus e to the power minus t. Okay. We want phi dot of 0 because phi dot of 0 is equal to a. So my a will be equal to 1 minus 1, 0, 2 into e to the power 0 is minus 1. Okay, minus 1 plus 3 minus 1, 0, 1. T is 0, t in 0 into anything is 0 plus e to the power minus t. So this is 1. Okay. So what will this value be? It will be minus 1 plus 3, 0 plus 0, 1 minus 1, minus 2 plus 1. Okay. So that is equal to 2, 0, 0 minus 1. Okay. For this system, which is given by x dot is equal to 1 minus 2, 3, 0, 2 minus 1, 0, 0, 3 into x. The zero input response will be a linear combination of what? Okay, what is the zero input response? Okay. So we have written question 1. Okay. So we look at question 2. Okay, we have x dot is equal to 1, 0, 0 minus 2, 2, 0, 3 minus 1, 3, 3 minus 1, 3 into x. Okay, here b is equal to 0. So this is an autonomous system. Okay, so there is no external input. Okay, and what you are asked is, what is the zero input response and what will it will be a linear combination of what? Okay, so this is first of all linear time invariant system, and you've been asked to find the zero input response. Okay, so that is basically your phi of t. That is basically your phi of t. Okay, because you know your x dot is equal to a t, a into x, and your x of t is equal to e raised to a t into x of 0. So that is your phi of t into x of 0. Okay. Now there is a property that your phi of t is a linear combination of the modes. What does that mean is this matrix over A, over here, our matrix A, okay, which is given by 1, 0, 0, minus 2, 2, 0, 3, minus 1, 3. Okay, it will have certain eigenvalues, right? If it is not repeated, then if they are distinct, if there's repeated with some multiplicity, etc., they can be there. It can be possible. And from those eigenvalues, we get the modes of the system. And then our phi matrix is a linear combination of the modes. So the modes depend on the eigenvalues. So what we have to do right now is we have to compute the eigenvalues of this. Okay, so how do you find the eigenvalues of this? So the eigenvalues is found using finding the determinant of lambda I minus a. Okay, so that is lambda minus 1, 0, 0, 2, lambda minus 2, 0, minus 3, 1, lambda minus 3. Okay, so if you find a determinant, this is lambda minus 1 into square bracket lambda minus 2 into lambda minus 3 minus 0, then minus 2 into 0 because of this, and this is minus 3 into 0. So that actually is equal to lambda minus 1 into lambda minus 2 into lambda minus 3. So this should be equal to 0. So we get our lambda is actually equal to 1, 2, and 3. So there are three distinct eigenvalues of this. Sorry. So there are three distinct eigenvalues. And what will be the modes? The modes actually will be e to the power minus t, e to the power t, sorry, e to the power t, e to the power 2t, e to the power 3t are the modes. Okay. So the phi of t will be a linear combination. Phi of t is a linear combination of e to the power t, e to the power 2t, e to the power 3t. So phi of t will actually be something like this. It will be some p1 e to the power t plus p2 into e to the power 2t plus p3 into e to the power 3t, where p1, p2, p3 all they are matrices of dimension n cross n, and here n is actually 3. So p1, p2, p3 are square matrices of dimension 3 cross n, 3. Okay, and phi of t is a linear combination of this. Okay, like over here, right? This is my phi of t. Okay, so one thing I'd like to point out is, if you notice, this A is an upper triangular matrix. It is an upper triangular matrix. And because it is an upper triangular matrix, these, what do you say, these diagonal elements, they are the eigenvalues. Okay, they are the eigenvalues of this matrix. Okay, this is happens for upper triangular matrix. It can also happen for a lower triangular matrix as well as for a diagonal matrix. Okay, so if this question comes in the exam, you don't need to, find the eigenvalues and then you have to find the modes and then you will say it is a linear combination of this. You have to work fast. Okay, you have to do things fast. So there's this property. Okay, this is a very nice property. So you must learn to take the question, look at it, observe the question, see if there is any property which is clicking. Okay, how to know what is the phi dot of t, what is phi of t, etc. That's how you learn and integrate it. Okay, and the assignment questions are very good. If you solve it, it is giving you more, insight into what you have learned. Right. So this is how it is a linear combination of these modes. Okay, it's a linear combination of these, which are your modes of the system. Okay. So now, and we look for the next question. Okay. Sorry. So an LTI system is given below is relaxed. It is not related. It is actually relaxed at t equal to 0. What will be the response for u of t equal to e to the power minus 2t? Okay. This is what we have to look at. Hmm. So this is my question 3. Question 3, x dot is equal to what? 1 minus 1, 2 0, 2 0 x plus 1 0 u, 1 0 u, sorry, and y is equal to 0 1 x. Okay, so this is the system, and what they are saying is it is relaxed. It is relaxed at t equal to 0. And your input u actually is e to the power minus 2t when t is greater than 0. And they are saying the system is relaxed. Okay, so when we think of relaxation, we think, okay, peaceful, nice, etc. So what do they mean by system is relaxed in this context? Okay, in the context of this system and this state and the context of this question. So if you will see, this is a system of order 2. Okay, so this is my state vector. It has x1 and x2. Okay, that's why it is a column vector of dimension 2, two elements. Okay, now there's x of 0. Okay, so this is x1 at 0 and x2 at 0. Okay, what they have told is the system is relaxed. If the system is relaxed means there's no energy stored in the system, and that means currently these initial states are at 0 and 0. Okay, so x1 of 0 is 0, x2 of 0 is 0. So this is the initial condition. So my initial condition is 0. Now we know my response x of t is what? E to the power 8t x of 0 plus integration of 0 to t e to the power a into t minus tau into b into u of tau into d tau, right? Now since my x of 0 is 0, my x of t is just basically what? 0 to t e to power a t minus tau b u of tau into d tau. Okay, so this is my x of t. Now, how do I solve this complicated, integration? Okay, I have to find the exponential of a matrix, then I have to multiply with another matrix, then I have to integrate it with time, and this is with respect to the variable tau. Okay, tau is varying from 0 to t. Okay, so how do you do that? So basically, if you look at it, this is actually a convolution. This is a convolution in time domain. But if you go to frequency domain on Laplace transform, then it is like the response of a system. Okay, it is like the response of the system. So if we want to find the response, this response, we have to go for Laplace transform. Okay, we have to do what is known as the Laplace transform. And if you remember the definition of transfer function, when we will consider what is a transfer function, we make an assumption. And what is that important assumption is? The assumption is that the initial conditions are 0. Okay, the initial conditions are 0. And that is given to us. So what we have to do is we have to find the Laplace transform and take the inverse Laplace transform. We will get our x of t. Okay. So we have to do that. So what we will do is, so this is our A matrix, this is the B matrix, this is the C matrix, right? So we have, we will first, we know that our x dot is equal to ax plus bu, right? So if we take the Laplace transform, it is what? S into I into x of s is equal to a into x of s plus b into u of s. Okay, that is si, sorry. It actually is si into x of s minus x of 0 minus. That's the initial condition. Into a into x of s plus b into u of s. Okay, so this in our case is 0 because we are told that the system is relaxed, right? So we get si into x of s is equal to a into x of s plus b into u of s. So that actually is si minus a into x of s is equal to b into u of s. So that's why our x of s is actually equal to si minus a inverse into b into u of s. Now, our y is equal to cx, right? So our y, of s is actually c into x of s. So that is c into si minus a inverse into b into u of s, right? So this is what we have. So now let us try to find si minus a inverse. So si minus a actually is what? S into 1001. And what is our a? Let us look at the question here. So a is what? 1 minus 1, 2, 0. 1 minus 1, 2, 0. Right? So that is s minus 1 minus 2 plus 1 and s. So this is si minus a. So what is mod of si minus a? That actually is s minus 1 into s plus 2. That is s square minus s plus 2. So our si minus a inverse actually is equal to, we interchange the diagonal elements, so it becomes s, s minus 1, and the off diagonal elements, we change their sign. So it becomes 2 and minus 1 divided by the s mod of si minus a, determinant of si minus a, that actually is s square minus s plus 2. Okay. So this is what we get, right? So this is our si minus a inverse. Now what we will try to find. Our u of t actually is e to power minus 2t. So u of s actually is equal to 1 upon s plus 2. Alright, u of s actually is 1 upon s plus 2. So let us find what is the y of s. So y of s is what? C into si minus a inverse into b into u of s. So what is c? Our c is, sorry, 0, 1, 0, 1. Si minus a inverse is what? S2 minus 1, s minus 1. The whole thing divided by this s square minus s plus 2. Okay, what is b? B actually is 1, 0. So this is 1, 0 into 1 upon s plus 2. Okay, so what happens is 0 into 1, so this becomes minus 1. And this actually is s minus 1 upon this s square minus s plus 2 factor, and 1, 0 matrix into 1 upon s plus 2, right? So this becomes equal to what? Equal to minus 1 upon s square minus s plus 2 into 1 upon s plus 2. So this is what is the response, y of s. Now we have to find y of t. Okay. So how do we write 1 upon s square minus s plus 2? Hmm. Four AC, so minus 8. So actually it becomes imaginary and it is a bit complicated. So what our y of t is actually what? The inverse Laplace transform of this. So this is our y of t. Okay. There is a way for MATLAB itself to find out your inverse Laplace transform. So let us look at it. Let's see, inverse Laplace transform. Okay, so what is our system? What do we have? I'll use the symbolic math toolbox. So I'm defining symbols S and T. Okay. So my function, my f of f actually is equal to what? Minus 1 on s raised to 2 minus s plus 2 into s plus 2. Okay, so this is my function. Let me run this. So this is my f. So I have to find the inverse Laplace of f with respect to t. So I'll run the section. So this is the inverse Laplace transform. So actually it is very complicated, right? That's why I didn't do it. So this is how you can actually use MATLAB to solve, okay, and to check your answer, right? So let us do from the start. Okay, what is my A matrix? The A matrix in this case is 1, 2, minus 1, 0. 1, 2, minus 1, 0. So this is the A matrix. What is my B matrix? It is 1, 0. So 1, 0. What is my C matrix? I think it is 0, 1. So 0, 1. So this is my C matrix. Right? So my transfer function actually is what? C into S into the identity matrix minus A, right? Into B. So let us run this section. What do we get? So this is the transfer function which we also got, right? And our U actually is E raised to minus 2 into T. So our U of S in Laplace domain is Laplace of U. Let's see what it comes. Oh, exponent. So run the section. So U of S is actually 1 of S plus 2, right? So our F actually is what? The transfer function into U of S. So our F comes out to be like this, and our inverse Laplace transform comes out to be this. So this is basically our response. Okay, what was the question? The question told we want to find the response. So the initial condition is 0. So I can just apply the Laplace transform and I can get this equation. Okay, and so there's this code also is there, which I've written. Okay, so for this, the inverse Laplace transform was computed by MATLAB. Okay, so power of MATLAB is there. Like you're doing some steps, but you don't know whether it's correct. You have found the inverse Laplace transform and you want to check again. Okay, so this power is there in MATLAB. You should use it. And in this age of AI, there are many ways for you to verify whether your answer is correct or not. Right? So now let's go move on to the next question. There's a system which is given by this matrix, and we have to find a discretized form of the state equation. And we are considering what is known as a zero order hold. Here, zero order hold is considered. So it is talking of a zero order hold, right? So I have a system that is given by x dot is equal to ax plus bu. I want to discretize it considering ZOH. Okay, zero order hold. It is written as ZOH many times. Okay. So what do we do then? We know x of t is actually e to power a t x of 0 plus integration of 0 to t e to power a t of minus t minus tau b u tau into d tau. Okay. So this is the equation. When we go for discrete time, our this x dot equal to ax plus bu gets written as x of k plus 1 is equal to a into x of k plus b into u of k, right? So now there is a sampling period. Sampling period at which rate I'm sampling, that is given by time tau, capital T. Okay. So now what is this? I'm going from x0 to some x value, okay, to some x t. So this actually is my x k to x k plus 1. Okay, x k plus 1, right? So how will I write it out? As my x k plus 1 is equal to e to power a capital T x of k plus integration is going from 0 to t e to power a t minus tau b uk into d tau. So what I assume, because it is a zero order hold, I'm holding the input at a fixed value. So it is stuck at uk. Okay, so uk is no longer a function of tau. So we can write it as xk plus 1 is equal to e raised to at into x of k plus e to, and this is a function of tau, okay? It becomes written as e to power at into b into u of k. Don't know whether I can remove it out. Okay, so let's not do that. E to power at, tau goes from 0 to t, e to power minus 8 tau b into u into d tau. Okay, this has come outside, right? So now I have to integrate this. So it becomes xk plus 1 is equal to e to power a t xk plus e to power a into t into e to power minus a tau upon minus a, and tau is going from 0 to t. Okay, p into uk. So that xk plus 1 actually is e to power a t x of k plus a inverse into e to power a t, right? Our a t actually should be capital T over here. Sorry, it's capital T, capital T, capital T into e to power minus a tau 0 to t b of uk. So xk plus 1 actually is equal to e to power a t xk plus inverse of a, sorry, a inverse e to power a t into minus e to power minus a t plus I. Okay, into b into u of k. So that xk plus 1 is actually e to power a t xk plus a inverse e to power a t minus I into b into uk, right? So this minus and this, so e to power at minus e to power e raised to minus 80, so it becomes minus I, and here I into e to power 80, so it comes out like this. Okay, so this, when we compare it to our xk plus 1 equal to ak a into x of k plus b into u of k. Okay, a discretized, b discretized. So our discretized a matrix is actually e to power at, and our discretized b matrix is a inverse e to power at minus I into b. Okay, so these are discretized B matrix. All right. So now what can we do with these matrices? How do we find these matrices? Okay. E to power at, we can use MATLAB and we can do it. Right. Or you can use the Laplace inverse transform and you can get e to power at. And BD you can find using this method. Okay, once you find e to power at, you have to just substitute the value here, subtract by I, and we find A inverse and B. Okay, so this is a way to do it. So let us consider the matrix which we have considered for our sum. Let us go to our question. That will be which question? Be question 4. Question 4. Okay. Here x dot is equal to ax. This is minus 1, 2, 3, 5 x plus 1 to u, 1 to u. Okay, we have to find the discretized matrices using zero order hold. Okay, so this A, B, we have to find AD, which is actually e to power at and BD, which is actually A inverse e to power at minus I into B. Okay. So what we will do? Let us consider t is equal to 1. T time, we are sampling it at a rate of 1 second. Okay, let us assume t equal to 1 second. Now, how do you find e to power at? So again, we can do the SI minus A, etc. That method we can apply, right? So now I've already showed how to do it for a second order system with Laplace transform. You can do it for a manual calculation. For ease of speed, let us try it using MATLAB, right? So this is the A matrix, right? This is the A matrix which we have. A is given over here. Let's remove this, put this. Okay. So this is the A matrix minus 1, 3, 2, 5. We have this is the B matrix 1, 2. Time is 1 second. So what is my phi? This actually is my discretized A. A discretized. This exponential of the matrix A into T. And my B discretized is equal to inverse of A into exponential of A into T minus I into B. So just running this, I get my discrete time A matrix and my discrete time B matrix. Okay. So this is a very simple and easy way to check your answer. Okay. Because in the exam, you will not have MATLAB to help you. So you have to manually do it. Okay. So manually, let us try to do it fast. So what is S I minus A? So that is S plus 1 minus 2 minus 3 S minus 5. If this is Si minus A, what is Si minus A inverse? That actually is equal to S minus 5. We interchange the diagonal elements and change the sign of the off diagonal elements. And then we multiply it, say S minus 5 into S plus 1, right? So S square minus 5S plus S minus 5 minus 6. So Si minus A inverse actually is equal to S minus 5, 2, 3, S plus 1 into S square minus 4S minus 11. Okay, so this is the Si minus A inverse. Now you have to find e to power 8t, right? Okay. So this actually should be Si minus 8t. And since our t equal to 1, this is fine. Otherwise, we'll have to again redo it. Okay. So our e to power at is actually what? The Laplace inverse of this. That is the s minus 5 s square minus 4s minus 11. 2 upon s square minus 4s minus 11. 3 upon s square minus 4s minus 11. S plus 1 upon s square minus 4s minus 11. So since this matrix I have chosen arbitrarily to find the Laplace inverse is difficult. It is not in the standard form. So what can we do in this case is, we have e to power at, right? Let us write it as I plus a into t plus a square t square upon 2 factorial plus a cube t cube upon 3 factorial plus dot dot dot. Okay, we can try to write it as this format. And since t equal to 1, we can write it as I plus a square upon 2 plus a cube upon 6 plus dot dot. Okay. So what is our a? What is our a square? A square actually is equal to what? What is A? Minus 1, 3, 2, 5 into minus 1, 3, 2, 5. Okay. So minus 1 into 1 is 1. Plus 2 into 3 is 6. Okay. Then again, minus 1 into 2 is minus 2. Plus 2 into 5, 10. So minus 8. So plus 8. 3 into minus 1, minus 3. Plus 5 into 3, 15. So 12. 3 into 2, 6. Plus 25. So that will be 31. So it actually is equal to 7, 8, 12 upon 31. Right? Now let's check what is our A cube. That is A square into A. So that is 7, 8, 12, 31 into minus 1, 3, 2, 5. Right? So that is minus 7 plus 24. So what is minus 7 plus 24? So that is 17. Then 7 into 2 plus 8 into 5. 14 plus 40 is actually 54. 12 into minus 1 minus 12 plus 3 into 31. 31 is 93 minus 12. So that is 81. 93 minus 12 is 81. Right? Then 12 into 2 is 24 plus 31 into 5 is 155 plus 24 is 159, 179. Okay. So this is what we got our A cube to be. Okay. So now what is our e to the power 80? That is what I plus A plus A square upon 2 plus A cube upon 6. Right? That actually is equal to what? 1001 plus A. What is our A? Minus 1, 3, 2, 5. Plus A square upon 2. A square upon 2 is what? 7 by 2, 4, 6, 31 upon 2. Right? Plus A cube upon 6. So 17 upon 6, 54 upon 6, 81 upon 6, 179 upon 6. So if you add them, what will you get? E to the power 80 is calculator. 3.5 plus 17 upon 6. That comes over to be 6.3333. Then 0 plus 2 plus 4 plus 54 by 6 comes out to be 15. Then 3 plus 6 plus 81 upon 6. That comes out to be 22.5. And 1 plus 5 plus 31 by 2 plus 179 by 6. That comes out to be 51.33. What is the answer we got? Is 40 and 91, 137 and 312. So there is a marked difference because we have taken only to a limited order. We have only taken to A cube by 6. So you'll have to take from higher order, or a better approach would then be to just find the inverse Laplace transform of this, right? The inverse Laplace transform of this. Okay, so this is a bit complicated. So now let's go to the next topic. Okay, so we have to do discretization using Euler's approximation. So in the previous case, it was very difficult because we had to find this e to power at, and that is very hard to analytically calculate. Okay, it is very difficult. Inverse Laplace transform is one way, or this is another way, right? Okay, so all these you will need to use for these calculations. You will need to use numerical methods. It is not possible to do hand calculations all the time. And I think when the professor will give you sums in the exams, he will give you simple sums. Okay, where there's 8t and this a square, a cube also will have certain nice characteristics they will have, so that it is easy for you to formulate it. Okay, so that or there are various methods like you find a Jordan form and then you do the powering, squaring, cubing, etc. All that there are various methods are there, but we will not look into all that. So let us consider for Euler's approximation. So we have x dot is equal to ax plus bu. Okay. So what does Euler say is this derivative, you will write it as xk plus 1 minus xk upon t. Okay, this actually is equal to ax plus bu. So what he's doing is approximating x dot by this. Okay, and can we do it? We can if this t is very small, then it will, can accurately represent. So what do we do then? Our xk plus 1 minus xk is actually a into t into x plus b into t into u. So our xk plus 1 actually is what? It actually is equal to xk plus 1 is actually equal to xk plus a into t into x plus b into t into u. So we can write xk plus 1 is actually I plus at into xk plus bt into uk. So this is our discretized matrices. So using Euler's approximation, we can write a discretized A matrix is actually I plus at and bd is actually equal to b into t. So this is a quite simple one. And this is something you can analytically calculate as well. So let us consider what we have considered. So this is what we have. So A is actually equal to minus 1, 3, 2, 5, right? And B is equal to 1 and 2, right? So our AD actually is what? I. So that is 1, 0, 0, 1 plus A into T, that is minus 1, 3, 2, 5 into T, right? So that is 1, 0, 0, 1 plus minus T, 2T, 3T, 5T. Okay, so that actually is what? 1 minus T, 2T, 3T, and 1 plus 5T. Okay, so these are AD. And what is our BD? BD is what? B into T. B is given by the expression 1, 2 into T. So it is what? 2 into 2T. So, so what you must understand is A and matrix, B matrix are for the system, for the continuous time system, and AD and BD is for the discretized system, but they depend on T. They depend on T. So if you change T, AD and BD will change. So what we can write is AD actually is dependent on T, so it is a function of T. And BD also is a function of T. So if we want to be accurate, when we use this Euler's approximation, accuracy is possible only if t is small. If t is large, that is the time period is large, then it is very difficult for us to get accuracy, right? Okay, so this is one thing. The next, let us consider, so this is for Euler's approximation. And let us consider this difficult, challenging thing. Okay, we want to find the fundamental matrix and the state transition matrix for this system. Okay, so now we are going into the domain of linear time varying systems. That is LTV. Okay, it is a linear time varying system. So what we have, our x dot is actually equal to 0, 0, t into 2 into x. Okay, so this is our system. We want to find the fundamental matrix. And the state transition matrix. Okay, so how do we do this? We know x is a vector of x1, x2, right? So x dot is what? So this is x1 dot, x2 dot is equal to 0, t, 0, 2, x1 into x2, right? So we can write our x1 dot is equal to t into x2 and our x2 dot is equal to 2 into x2, right? Now, how do we solve this now? So we write our x2 dot minus 2x2 is equal to 0. So this actually is what dx2 by dt plus minus 2 of x2 is equal to 0. So if you remember, we used to have these equations like dy by dx plus py is equal to q and y into integrating factor is equal to integration of q into integrating factor plus c, etc. Right? So if we do that, our x2 into the integrating factor will be what? E raised to p into dx. Okay. So for our case, integrating factor is equal to e raised to minus 2 into dt. So it is e to the power minus 2t. So our solution is x2 into e to the power minus 2t and q is 0. So it is 0 plus c plus c. Okay. So our x2 is actually what? C into e to the power 2t. Now when we put t equal to 0, so this x2 of 0 is equal to c. So therefore our x2 is what? x2 0 into e to the power 2t. So x2 0 is the initial condition. This is the initial condition. So this is the expression for x2. Okay. So this is the expression for x2. Now what is x1 dot? x1 dot is equal to t into x2. So that is equal to t into x2 naught into e to the power 2t. Right? So this is our x1 dot. So now we have to integrate this, right? So this is dx1 by dt is equal to x2 naught into t e to the power 2t. So our x1 is x2 naught integration of this t into e to the power 2t into dt, right? So how do we integrate this? So if I'm not wrong, we have to do integration by parts. And Bindu, do you know integration by parts? Because I don't remember it. I've done it long ago. What is the thing for? There is
Sir,
a
I too
formula.
forgot, sir. Sir, can we use the Laplace transform method, sir?
You cannot use Laplace transform here because it is multiplication. So when you do Laplace transform, like multiplication in time domain, gets converted into convolution in frequency domain. So you cannot exactly use Laplace transform here. What is the
Okay, sir.
what is integration of u v is integration of v minus integration of du by dt. I think it is this. I think it is this. So let's try. So x1 is x2 naught integration of t e to power 2t dt. So let us integrate this. Integration of t e to power t 2t dt is actually is u. Lie 8. Lie 8. So e is exponential is the last. So first we will do this expression, algebraic expression. So this t e to power 2t into dt minus derivative of this, so dt by dt. So by here my u is t and my v is e to power 2t. So this is Lie8 is the order. Okay, so logarithmic, inverse, algebraic, trigonometric, exponential. Exponential is last, so that's why I give v equal to e to power 2t. So that is, so this t integration of e to power 2t dt minus dt by dt, integration of e to power 2t into dt, and the integration of this entire thing. So that is 2 e to power 2t upon 2 minus integration of dt by dt is 1, and e to power 2t integration of it is again e to power 2t upon 2 into dt. So that becomes 2 by t by 2 e to power 2t minus e to power 2t upon 4. Okay, so this is the expression. And we must also consider an initial condition. So let us consider initial condition C. Okay, so this, so our x1 is actually what? x2 0 into t by 2 e to power 2t minus e to power 2t upon 4 plus c. Okay. Now let us consider time t equal to 0. So that is x1 0. So x1 0 is what? x2 0 and t 0. So this is 0 minus 1 by 4 plus c. Right? So x1 0 upon x2 0 is equal to c minus 1 by 4. So c can be written as 1 by 4 plus x1 0 upon x2 0. Right? So our x1 of t is actually equal to x2 0 into t by 2 e to power 2t minus e to power 2t upon 4 plus c, that is 1 by 4 plus x1 0 upon x2 0. So our x1 of t is actually equal to x2 0 t by 2 e to power 2t minus e to power 2t upon 4 plus 1 by 4 plus x1 0. Okay, so this is the expression of x1 t and this is so this x1 t is this expression, and our x2 of t is given by the expression x2 0, so x2 0 into e to power 2t. This x2 0 e to power 2t. So these are the two equations of x1t and x2t as functions of time and of initial condition. So now you have to find what is, if you look at the question, you have to find the fundamental matrix and the state transition matrix. So we have to find the fundamental matrix. So the fundamental matrix is not unique. Okay, it is not unique. It depends on the initial condition you choose. Okay, so which initial condition should I choose? Okay, so usually what they choose is, so fundamental matrix actually is a n cross n matrix, and in our case n is equal to 2. So let me just show by example, then it becomes easier. So what they do is, we have x1 0, x2 0. These are our initial conditions, and this is our x1 t, x2 t. So based on the initial conditions, what are these values? So let us consider x1 0 is 0, sorry, 1 and 0. If x1 0 is 1 and x2 0 is 0, then what will happen? Then my x1 of t is what? x1 0, because x2 0 is 0. So this is 1 and this is 0. So this is an easy way to make it compact, okay, to make it simple. Similarly, if x1 0 is 0 and x2 0 is 1, then what will happen over here? My x1 t will be what? T by 2 e to power 2t minus e to power 2t upon 4 plus 1 by 4. And x2t is what? E to the power 2t. Okay, so this is the matrix I get. So the fundamental matrix actually is equal to this 1 0 1 0, and this t by 2 e to power 2t minus e to power 2t upon 4 plus 1 by 4, right? And e to power 2t. So this is the fundamental matrix. Now, what is the state transition matrix? What is state transition matrix? So let us say this is like something v of t. Okay. So state transition matrix is actually the inverse of v of t into v of t0. Okay. So t0 is some initial time. Okay, the initial time. It is represented as t0, right? So what is v of t0? Is 1 0 t by 2 e to power 2t minus e to power 2t upon 4 plus 1 by 4. Okay, everywhere t is there, we have to replace by t0 into e to power 2t0. Okay, so now we have to solve this. Okay, how do we solve it? Our first I want to find the inverse of v of t, right? So let me see, v of t is, this is my v of t, right? So I will interchange the diagonal elements. So that will be e to power 2t and 0. And the off diagonal elements, I will change their sign. Okay, actually, sorry, this is 1. This is 1, right? Off diagonal elements, I will change their sign. So it will be minus 2 by 2, minus 2 by 2 e to power 2t plus e to power 2t upon 4 minus 1 by 4. And this is 0. Take this into the determinant. The determinant is what? E to power 2t, e to power 2t minus of 0. So it is 0. So this is e to power 2t. So the inverse of v of t is actually 1 0 minus t by 2 plus 1 by 4 minus e to power minus 2t upon 4 into e to power minus 2t. So this is inverse of v of t, right? So now the state transition matrix is actually the inverse of v of t into v of t0. So that is 1 0 minus t by 2 plus 1 by 4 minus e to power minus 2t upon 4 e to power minus 2t into v of t0, that is 1 0 t by 2 e to power 2t0 minus e to power 2t0 by 4 plus 1 by 4 into e to power 2t0. Okay. So if we multiply this, it is a very long thing. So 1, this into 0, so it is 0. The next I multiply 1, so that is t by 2 e to power 2t0 minus e to power 2t0 by 4 plus 1 by 4 minus of this, right? So this will be minus t by 2 e to power 2 t0 plus 1 by 4 e to power 2 t0 minus e to power minus 2 2t plus 2 t0 upon 4. So this is one side. Now 0 into this, 0 and 0 into this, so this is 0. This is e to power minus 2, 0 into this and again into this, so it is e to power 2 t0 minus 2t. So our state transition matrix effectively becomes 1, 0, t by 2 e to power 2 t0 minus e to power 2 t. Okay, so let me check. This 2 by 2 e to the power 2 t0 minus t by 2 e to the power 2 0. How did this come like this? Okay, so they get cancelled. This and this get cancelled. This also gets cancelled. And this is 1 by 4, right? 1 by 4. How did this come? It is 1 into this. So 2 by 2 into e to the power 2 t 0 minus e to the power 2t plus 1 by 4 plus e to the power 2 t0 into this. So this minus 2 by 2 e to the power 2 t0 plus 1 by 4 e to the power 2 0 minus e to the power minus 2t plus 2 t 0 by 4. Okay, so this is actually, so this get cancelled, right? So it becomes 1 by 4, sorry, 1 by 4, 1 minus e to the power minus 2 into t minus t0. Okay, so this is the matrix and this is e to the power 2 t0 minus t. So I can further write it down as 10.25 1 minus e to the power 2 t0 minus t into e to the power 2 t0 minus t. Okay, so this is the state transition matrix. So what I have done is I have used MATLAB symbolic mat toolbox. Okay, so this I'm just using to verify my calculations, and I think there is some mistake, but we have to again check carefully. Okay, where I made a mistake, I'll have to check. So this is the symbolic mat toolbox. I'm defining variables t and t naught. Okay, so they are not showing here. So these are the variables t and t naught, and this is x1 state 1 as a function of t and x2 also as a function of t. And x1 0 and x2 0, these are the initial conditions. Okay, I've defined initial conditions as symbolic variables. So now this is the vector. Okay, x1, x2. This is the state vector. x1, x2, right? And this is the A matrix 0t and 0t. So this is the system matrix, right? So now this is the x dot. What is my x dot? Is the derivative of x with respect to t. Okay, this is the derivative. Derivative of statement. Okay. So now I will define the initial conditions that x10's initial condition is given by x10 and x2's initial condition at time t0 is x20. Okay, and I'll say that my equation is x dot, that is the derivative of x with respect to t, is equal to a into x. And tell them, then I'll tell it you solve it. And once it solves, it gives this expression. So x2 is what? x20 into e to power 2t, and x1 is x10 plus x20 by 4 plus x20 into e to power 2t into 2 into t minus 1 by 4. So let us see what I have got. So x20 is what? x20 into e to power 2t, which is correct. And x1 of 0 is what? It is x10 plus x20 by 4. Till that is correct, right? Plus x20 into e to power 2t into 2t minus 1 by 4. Okay, so that also is correct. So x1 also is correct. So it is given by this. So x1 solution is what? x10 plus x20 by 4 plus x20 into e to power 2t into 2t minus 1 by 4. So here I can write it as this one, pen. This can be written as x1 of t can be written as x10 plus x20 by 4 plus x20 by 4 into e to power 2t into 2t minus 1. Okay, so this also has been found by this equation, right? This is the equation x20 into e to power 2t into 2t minus 1 by 4. Now, I will find what is x1 and x2 for the first initial condition, that is 1 and 0. Okay, so we found over here, we found it. This is 1, 0. So this is my variable x1 sub a, x2 sub a. This is the a case a. So this is what? Case a, and this is case b. So then similarly I do it for case b, where I substitute it by 1 and 0. And then I will get this equation. So my x1 sub b is what? E to power 2t into 2t minus 1 by 4 plus 1 by 4. And x2 sub b is e to power 2t. Let us check. So this actually is e to power 2t is coming correct. So here is 1 by 4, which also I got, plus 1 by 4 into e to power 2t into 2t minus 1. So they have just written in a better form. They have written this as 1 by 4 plus 1 by 4 e to power 2t into 2t minus 1. Okay, so this also is correct. This also is same. 2t minus 1. It is also correct. Now, what we have to find, the fundamental matrix is given by this expression. So let us see what is the fundamental matrix. The fundamental matrix comes out again as this format. So that is what? 1, 0, divide, and again this. E to power 2t, 2t minus 1 by 4 plus 1 by 4, and e to power 2t. So this is the fundamental matrix. Then, okay, the mistake which I have made is something else. So initial t0 is what? I will substitute in this fundamental matrix, I will substitute value t0. So this is our v of t0. So this is v of t0. So v of t0 is the initial t0. Okay. So 1, 0, and wherever t is there, replace it by t0. Okay. E to power 2 t0, 2 t0 minus 1 by 4 plus 1 by 4 into e to power 2 t0. So this is the initial one. Okay. Initial matrix. And actually the state transition matrix is the fundamental matrix into the inverse of this initial t0. What I did was I took the inverse of the fundamental matrix into initial t0. So let me correct myself. Okay. So this is the error. So this is the mistake which was made. So that's why this is wrong. So the state transition matrix is actually given by this formula. It is the fundamental matrix into the inverse of v of t0, right? So that is v of t into inverse of v of t0. Okay. So what is the inverse of v of t0? So what is v of t0? V of t0, actually, if we will see what is v of t0, it is 1, 0, t by 2. So let us write it in a very compact form. So it is 1, 0, 1 by 4 plus e to power 2t upon 4, 2t0 upon 4 into 2t0 minus 1. Okay. So this is v of t0. So 1 by 4 plus 1 by 4 into e to power 2t0 into 2t minus 1. And over here it is e to power 2t0. Okay. So inverse of v of t0 would be, so e to power 2t0 comes here and 1 will come here. And you interchange the sign of the off diagonal element. So this becomes 0. So this will become 1 minus 1 by 4 minus e to power 2t0 upon 4 into 2t0 minus 1. Okay, so this is the inverse of v of t0, right? Upon e to the power 20, e to the power 2t0. And this 0 into this, so it becomes 0. So this becomes, so your inverse of v of t0 actually is equal to 1, 0, minus 1 by 4 e to the power 2t0 minus of 1 by 4 into 2t0 minus 1. And here it is e to the power minus 2t0. Okay. So it is minus 1 by 4 e to the power minus 2t0 minus 1 by 4 into 2t0 minus 1. And here e to the power minus 2t0. Okay. So now, what is the state transition matrix? State transition matrix is what? V of t into inverse of v of t0, right? So what is our v of t? Our v of t is actually 1, 0, 1 by 4 plus e to the power 2t upon 4 into 2t minus 1. And here it will be e to the power 2t. So this is our v of t into the inverse of v of t0, that is again 1, 0, minus 1 by 4 e to the power minus 2t0 minus 1 by 4 into 2t minus 1 into e to the power minus 2t0. Okay. Now we have to do this calculation. So that our state transition matrix will be equal to 1. So 1 into 1 is 1 and this into 0 is 0. So 1. Similarly, 0 into 1 is 0 and e to the power 2t into 0. So this is also 0. Now the trick is 1 into this and this into this. So 1 into this will be what? Minus 1 by 4 e to the power 2t0. Okay, this is our bracket. This is 1, this is 1, and this is 1. So minus 1 by 4 e to the power 2t0 minus 1 by 4 into 2t minus 1, right? Plus this. Plus 1 by 4 into e to the power minus 2t0, 1 by 4 e to the power minus 2t0 plus e to the power 2t minus 2t0 upon 4 into 2t minus 1. Okay. So this is this. And then we have this 0 into this is 0 and e to the power 2t into e to the power minus 2t0. So that is e to the power 2 into t minus t0. Okay, it comes out like this. So now what do we do? So this minus 1 by 4 e to the power 2t0 and 1 by 4 e to the power minus 2t0, they get cancelled. They have to cancel out. This actually is e to the power minus 2t0, so this will be e to the power minus 2t0. So this and this will get cancelled. So matrix will become, state transition matrix will be 1, 0. So it will be 2t minus 1 by 4 into e to the power 2 t minus t0 minus 1 and then e to the power 2 into t minus t0. So this is a state transition matrix. And if you will look over here, this is the expression we got, right? So let me write it in this form of the simplified expression. I'll write it down as 1, 0, step by step. So this we got it as t by 2 e to power 2 t minus t0. This is 1 minus e to power 2 t minus t0 upon 4. Then minus t upon 2 plus 1 upon 4. And here e to power 2 t minus t0. Okay, so this is the expression we got, right? Okay, there's another error which I made sadly. So this actually is 2 t0 minus 1. So when we multiply, this actually be 2 t0 minus 1. So this also has to be minus t0 by 2 and here 2 t0. Okay, so that's why like when we manually calculate, it is prone to a lot of blunders. But here using MATLAB, we are able to get these simplified expressions. Okay, so I hope this is clear. Hmm. So thus we have considered various types. Okay, there are further questions. So there's this question and this question which you can go home, which you can try when you have time. Since we ran out of time, I can't solve these questions. But you can attempt these questions, or best you can start solving the assignment questions. So I think like after going through this doubt problem solving, doubt clearing session, you have the tools to tackle the assignment questions. So because I know the assignment questions are difficult and it is not easy to do it. So that's why I tried to came up like I tried to code it out so that I know and I can verify whether my answer is correct, etc. These are certain steps which are there, okay, which were useful for me, okay, useful because I need to be sure that my calculations are correct and I want to re-verify, right? So this is why I'm using this symbolic math toolbox, which is a toolbox of MATLAB. So if you have the what you say the license, to be very useful for you, right, to help you verify your answers, right? So I'll just do a brief recap of what and all I touched upon. Okay, we have solved a lot today. So I talked about what is a state transition matrix, and for a linear time invariant system, how x dot is equal to ax. This is an autonomous system, and x dot is equal to ax plus bu for a non-autonomous system. And then what is the state space solution? How do we write it down as? And how e to power at is a part of the state transition matrix. Okay, so this is our x of t in terms of the state transition matrix. And now knowledge of the state transition matrix is very important for us to be able to solve to find a state space solution, right? So this is 5 of t is e to power at. This is a. And how it is not simple. When you do exponential of at, it is not simple. Just you take the exponent of the terms. This is not the way. You either use the power series, which is shown over here. You use this power series, or you use what is the Laplace transform method. Okay. You have to take the inverse Laplace transform. You find the SI minus A, and then you have to find the inverse Laplace transform, and then you get your phi of t. Okay. So this is possible because they were simple and easy, but sometimes it is a bit complicated. So we have to check. I'll have to check what is a workaround for that, right? And now this phi of t is given by this expression. Phi of 0 is the identity matrix. This is I, which is this property is verified here. And similarly, phi of t is e to power at. The derivative of that is e to power e raised to at. And the derivative at 0 is equal to a. Okay, so this is another property which is a useful property, right? Okay. So now suppose this is a state transition matrix. Then how do we find a? So we have to find a derivative of the state transition matrix, substitute t equal to 0, right? And then we got a. Hmm. Similarly, question 2, in which we have to find the zero input response. Okay, this is an autonomous system, so there's no external input. So the output of the system is actually a zero input response. So that actually, it should be a linear combination of what? So it's a linear combination of the modes. And the modes are the determined from the eigenvalues. And since this is the upper triangular matrix, it is easy to compute the eigenvalues. So I've computed it, but we can directly write. Okay, it can be directly written. It can be directly written. Okay. So the phi of t is a linear combination of this. We have not done that, but it can be done. Okay. Similarly, this is a question 3 where we have to find the response of the system for this input, for this u of u input. Right? We consider that the system is relaxed. That means the initial conditions are 0. Okay. And then how we take the Laplace transform and then we can get a solution. So the issue here was the Laplace transform was a bit complicated, right? It was a bit complicated. So that's why the inverse Laplace transform is computed by MATLAB. There's a direct command in MATLAB to find the inverse Laplace transform. So, but these commands can be used by you only if you have the license for the symbolic toolbox, right? I hope you guys have it and you can try to get it. You can check, probably your college has the license and you can use it. Right? Then we consider what is the zero order hold, right? And how we can convert the continuous time matrix to a discretized version of the matrix, which is given by these expression AD is e power AT and BD is this. Then we try to do it. Again, we had to either find the inverse Laplace transform or we tried using the power series method, but it did not converge. Okay, it did not converge. So that I have to look into, like how to work around this. That if it is not converging, the power series is not converging, then what may be the issue? Hopefully in the exam, the matrix will be such that the power series will converge. But in the case of the matrix chosen by us, it did not converge. Right? There's another way to do discretization using Euler's approximation, which is given by this method. So derivative is given by xk plus 1 minus xk by t, right? And so this is the matrix AD and BD matrix. And this is simple. This can be analytically derived. Okay, but this depends. It is equal to only if t is small. Next, we consider linear time varying system. So till now it was linear time invariant system. That properties are much simpler. It is easier to compute and to find. But when we go to linear time variant systems, it becomes a bit complicated. So what was done, we had to find the solution of that, right? And then we had to do integration by parts. Okay, and then the integrated expression was found, right? And then we have to find the fundamental matrix. Although fundamental matrix is not unique, it depends on the initial condition I choose. I choose these initial conditions because it is 0. But probably you might have to choose some, good initial conditions such that you can cancel out something. All those things could be there, right? So you have to watch it. You have to be careful. There can be ways to get a simpler expression, right? It can be done. Then we found a state transition matrix. This was the mistake which I made, right? This is a mistake. So then I corrected it using this. Okay, it's actually fundamental matrix into inverse of V of Tz. So that was again computed and this expression was found and this was verified in MATLAB. Okay, so I hope this session was useful and I hope the MATLAB based verifications were also good for you guys. So hope to see you in the next class. So till then, thank you.